Hello, I'm Hyoungwoo Kim from KAIST, and actually I'm the PhD student, and my advisor professor is the Dongyuk Shin in here. And so now, okay, I'm going to present about the code coupling of PeleLM and IRL for liquid fuel combustion simulation. So, uh, yeah, this. Yeah, that's right also. And so this is just the schematic diagram of the liquid rocket engines in here. And so liquid fuel and liquid oxidizer go through this liquid pump and gas generator, and finally get into the combustion chamber. And in combustion chamber, the three processes are occurred, and one is the atomization process. And in this atomization process, the liquid reactants break up and form some small drumlets. And these small drumlets get some heat in the combustion chamber and become vapor in the vaporization process. And these vaporized reactants react each other and combust in the combustion process. So my final goal is to develop these full processes to simulate the liquid combustion. But in today's presentation, now I'm just going to focus on the automation process in the combustion framework. And so I use the two existing solver. One is the combustion solver PeleLM, which is the base of the AMREX, and the adaptive mesh low Mach number solvable for the reacting flows. And this solver was chosen because the ultimate goal is to solve the combustion, and this solver gives the full flow scheme of the framework of the flow scheme. And the other solver is the multiphase solver IRL. And IRL is also Baesh explained it for the previous case. And IRL is a library of the volume of fluid schemes for simulating multiphase flows. And it is necessary to, I think you can use. And I just start here again. So the second solver is the multiphase solver IRL, which already Maish introduced it. And this is a library of volume of fluid schemes for simulating multiphase flows. And it is necessary to interpret the interfaces of liquid and vapor. And it solves the volume of fluid equations in the flow schemes. And this simulation is using the IRL, which the robot did, to the liquid atomizations like this. And so in today's presentation, I'm going to talk about the PeleLM plus IRL code coupling. And this PeleLM plus IRL code keeps the interface sharp. And to verify this code coupling, I do the two test cases like this. And also, I want to introduce about some topology-based volume fraction correction. And this correction I use because to avoid the unreasonable errors. And to verify the correction, the three test cases are conducted. And so first is the PeleLM plus IRL code coupling. And so this is the original scheme of the PeleLM, which ignored the chemical kinetics. And so it first update the edge velocities, and it compute the velocities of flux of the velocity and flux of the density, and it update the next time step density. And finally, it update the next time step velocity. But here to couple with IRL, the new scalar field alpha need to be determined needed, and so the alpha means the volume of fraction, and so alpha equals 0 means there is no tracking fluid inside the cell, and alpha equals 1 means it is full with the tracking cell. And in the IRL can compute the flux of alpha with like this updating loop. If there is some alpha field like this, then the IRL reconstruct the interfaces like this, and finally it updated the flux of the alpha. And so in the coupled scheme of the PeleLM and IRL, instead of compute the flux of density, it compute the flux of alpha with using IRL, and then it update the next time step alpha, and using with this equation, it update the next time step density. And so to validate this coupling, first validation is the translation of the Zalesak disk. And so using this prescribed flow field, this Zalesak disk moves left to the right. And first, I'm going to show the results only using the PeleLM. It's not working, but if if it sees that the interface will not yes, not maintained it. Yeah, yeah. And if using the coupling PeleLM and IRL, and also is the result with the video, but I think it will not work. And so, if coupling do that, the Zalesak disk shape remains unchanged and keeps the interface sharp. And the second validation is the rotation of the Zalesak disk, and similar to the previous simulation, using the prescribed velocity field, this Zalesak disk rotated to counterclockwise direction, and finally it go to the original shapes. And also, this is also the video, but it not works. And if it rotated on one rotation with using the PeleLM only, then the shape is the sharp point shape becomes to the rounded, and the interfaces of the Zalesak disk becomes the radar, which means that the density is around 500. So the interface is not maintained it, but if I use the PeleLM plus IRL, also the video is not work, but this interface maintains like these shapes in this initial shape. And also I show some the shape error of the after one rotations, and you can see that the coupling with IRL significantly reduces the shape error. And then I'm going to introduce about the topology-based volume fraction correction. And this volume fraction correction is introduced because we found some unreasonable alpha distribution inside the drumlet. And this simulation is such a circular drumlet simulation, like the above image, but without using the gravity. So because there is no initial velocity and because of the surface tension, these circular drumlet need to be maintain the shape. But if I just do the simulation with using only PeleLM, then you can see that there is some volume fraction below than 1 in the 0.1 millisecond. And this non-unity alpha value grows like you can see in the 1 millisecond results. And we think that this is because of the fluctuating velocity appears near these interfaces, but the exact explanation need to be further studied. And so to avoid these unreasonable errors, the correlation is needed. So the topology-based volume fraction correction is introduced like these equations. So I use the product of the alpha neighbor, and where this alpha neighbor is the adjacent cell in for this problem, like this the central cell is the ijk cell, then the adjacent cell means the alpha neighbor. And if the product of the alpha neighbor is bigger than some epsilon, then changes this alpha to the 1. So in this study, the epsilon is used to 0 for a 2D single drumlet, and 0.2 is used for the other simulations. And and this is the results for the stationary circular drumlet, which I above shown in 2 slides before. And here for the without using the correction, the circle shape is deformed, and you can see some pink dot inside the circle, which means that cell's alpha value is smaller than 1. And also the pressure is not uniformed, but if we use the correction, the below result is using the correction, and the pressure is uniform, and the error rate with the theoretical pressure is 3.6%. And I also applied these results to the unsteady drumlet simulations. First is the 3D stretched drumlet, and using with these prescribed flow fields, this circular drumlet unstretched in the 1.5 seconds and go back to the initial shape in the 3 seconds. And this is the results without correction and with correction. And with using the correction, you can see that there are many dots inside the drumlet, which is the unreasonable result. But with using the correction, we can see that the circle shape is remained. And also this is the videos for without correction and with correction with the oscillating drumlet. And sorry for situation that I can show the results, but without using the correction, you can again show some drop holes inside the elliptical drumlet, and the elliptical drumlet's shape is not remained it. And using the correction, it oscillated well with, and the oscillation period agrees with the theoretical prediction by 6.7%. And so to conclude, I did the PeleLM IRL coupling, and the code coupling was validated with 2 cases, and the interfaces were preserved well. And the topology-based volume fraction correction is introduced to avoid the unreasonable results. And also, this correction was validated with 3 cases. And so now I'm doing is using this PeleLM plus IRL solver. I'm doing some oscillating liquid jet simulation, and also this video Mark shows to use. And for this video, the oscillating liquid jet is going to oscillating liquid jet is coming from this Z equal 0 domain, and this below graph shows the FFT results of the azimuthal instability following that the red planes. And also now I am implementing the vaporization model into this PeleLM plus IRL solver. And now I'm just doing the baby step of it. So this is some 1D Stepan problem for the validation. And because of this heated wall, the saturated liquid becomes the vapor, and the film of the vapor grows like it. And so this is also some video, but it's not work. But if it worked, that this blue liquid goes further too, and the vaporization film is gross. Oh, now this is work. Yes, but this is not working. Okay, thank you for listening to my presentation.
Questions? So in the one where the bubble got the dots in it, why did the dots form in the one that was just PeleLM?
I think this is supposed to be because of the we are now thinking that is because of the Gibbs phenomena of the velocity in the interface, and because this velocity made in like in this place, it makes some like velocity in these directions, so that the alpha value goes to below to the 1, and then if the alpha value is below than 1, the surface tension is calculated, and it makes that further below to the 1. And so I think that's why it makes some hole inside the drumlets.
You've got a pressure jump related to curvature.
Yeah.
Comes in momentum invection and causes it to mess up the invection of alpha.
As I think so, because of that.
Any more questions? Well, let's thank all our speakers again.